So we're going to use as our basis set for platinum, we're going to include 6s and 6p orbitals in addition to the 5d orbitals, so we can look at what the d orbital manifold looks like. Whereas for the hydrogen atoms, right, these are going to be 6s, 1s orbitals, okay? And so we can look at our relative energies for our atomic orbitals. So we're going to have our 2, 3, 4, 5. This will be our 5d or the energy levels for our 5d atomic orbitals. We have the 6s orbital, and then we have the 6p orbital right here. And these are low enough in energy, or these are close enough in energy that that's why we're including them in the basis set for our metal, for the platinum. Okay. Now, this is going to transform as T2G plus Eg. Okay, the atomic orbitals for the metal. This will transform as A1G, and this will transform as T1U. Right, mind you, we're in an octahedral. This is an octahedral complex, and so the character table, if we were deriving this using group theory, right, would be the O8 character table that we would derive this from. Okay. As for the hydride ligands, okay, we're going to generate symmetry adapted linear combinations of atomic orbitals from all 6s1s. Right, this is what these are going to look like. So we're going to have a set of 6 atomic orbitals, which we're going to generate 6 salks. So 1, 2, 3, 4, 5, 6. These are going to transform as A1G plus T1U plus EG. All right. Your A1G, so that we can take a look at what these look like, is if this is our octahedral, right, and the ligands are coming in on the coordinate axes here, right? We have 1s orbitals at each of the ends of each of the coordinate axes. This is your A1G. Okay. The T1U, the T is going to indicate that this is triply degenerate. Right? And so the T1U is going to look like this. Here's your T1U set. Okay. And then the EG, I'm just going to drop down here. It'll look like this. Oops. There we go. Rotated 90 degrees relative to the other one. And here's your EG salks. Okay. And mind you, right, there's no bonding between any of these 1s orbitals for the hydrogen, right? So these are all equivalent energy, okay? But they have different symmetries, right? So that transforms as the A1G plus T1U plus EG, okay? From there, right, and this should be, didn't draw this energy level correctly, but the relative heights here. Let me bring this down. The hydrogen atoms, right, are going to be lower in energy than our corresponding atomic orbitals for the metal. Okay, and that's very typical where the ligand orbitals are going to be lower in energy than the corresponding metal atomic orbitals. Okay, and that's important because when we're thinking about, for instance, the nature of the highest occupied molecular orbitals, we'll be thinking a lot about those having a lot of metal character rather than ligand character. Okay, so from there, right, we can construct our diagram using the principles that we've been doing. And so we have an A1G set, right, which is largely going to have ligand character of the hydride. Okay, we have a T1U set, right, which will have which will result from overlap of the ligand T1U salx and the 6p orbitals. It's the AG. So A1G, 1T1U. Okay, and then we're going to have an EG set derived from the EG salx and the EG orbitals. 1 EG. Okay. Right, from there, right, what we notice is that there's no corresponding symmetry of T2G for the 5D orbitals here. And so what we have then is our T2G set, our triply degenerate. We have a triply degenerate set of orbitals that have no corresponding symmetry from the hydrogen, the hydride salx. And so this is going to be non-bonding, right? And this is going to take the form of the DXY, DYZ, DXZ orbitals. So it's going to look just like the atomic orbitals for those, all right? From there, right, we have a anti-bonding pair. We have a corresponding anti-bonding EG. I'm going to denote that as antibonding with an asterisk here. The corresponding T1U antibonding, and then a corresponding A1G antibonding. Okay, the EG, right, is going to be derived. These are the corresponding orbitals here. T1U, whoops, T1U should be a lot higher in energy than all right, and then the A1G. Like this. 2T1U. Okay. And this gives us the this gives us what we expect for our ligand field diagram for platinum 4 hexahydride.